Next example, finding the centroid along the y-axis of this solid now. And what we do is we take a parabola z squared equals 100y, and we get the area. We have an area defined like so. And we revolve it in a circle so that it sweeps out a solid. And we want to know what the centroid is. Now, it's a mirror image around the z-axis, or the YZ plane. So that means that the centroid has to be at x equals 0. It also is a mirror image around the XY plane, which means the centroid along the z component of centroid is also 0. So x component and z component are 0. It's only the y component that might be non-zero, because we're not mirror imaging the object on the other side of the XZ plane. And we start out, we have this area, and so you have y as the centroid of the disk is y. The area of the disk times dy is dA. So this ought to be kind of easy. Now, there's a hard way to do it, and that is to think of it as concentric cylinders. Here, I'll draw it. I'll just draw it to sketch out the idea. I won't actually solve it that way. But think of it as, say, a cylinder, and you'll have a dr, and sweeping out a cylinder. So you can have expanding cylinders instead of moving the disk along. You can have an expanding cylinder going on. Now, then you'd have to find the centroid of the cylinder, which is going to be halfway between this point and this point. The centroid is going to be halfway between. The cylinder is uniform, but still it's a bit messy. dA would be 2 pi r dr. Then how do you express that in terms of the y coordinate? You have this anyway. It's not as easy. So we're not going to do it that way. We're going to do it the easy way. Okay, next slide. So as I mentioned, here's y bar dv. So it's pi z squared dy. And let's go back in just a second. Take a look at it. Yeah. So here's the z squared is 100y. 100y. So 100 pi y squared dy from 0 to 100 millimeters. That's the length. dv is just the pi z squared part. So it's 100 pi y dy. So it's, the 100 pi's cancel out. You'll have 100 cubed millimeters cubed over 3 on the top, divided by 100 millimeters squared over 2 on the bottom. So factors out, you're going to get 2/3 of 100 or 66.7 millimeters. Okay. Looks really complicated, not too hard. Okay, now This turns out to be the same problem, folks, that the density varies. Now, the density is not constant. We have to go back to what do we do when it's not constant? And the centroid, the x component, the y component of the centroid, because of symmetry, would have to be at 0. It's only z which can change, the z centroid. So dv is pi r squared dz, just like before. 0.5 meters is the radius. So pi r squared dz is going to be dv. So integral z hat rho. Now, we got to keep the rho's. Because they're changing. It's a function of z now. It's a function of z. It's not a constant. They don't factor out because the rho is not a constant. So you got to leave it in. Leave it in here and here. Pi r squared dz, that's the differential volume. And then this is the how everything works. Now, a couple of things do factor out. These constants, the 200 constant. So we're going to get, and the pi's. So we're going to get z squared dz on the top, z dz on the bottom. That would be 1/3 on the top, 1/2 on the bottom, right? Because the limit is 1, or 2/3 of the total height, 2/3 of a meter. Check. Okay. Now, if you have composite bodies, it's just like the beginning. You take the sum over all the individual bodies that you have. This is the centroid of that body times the mass of that body divided by the total mass, the mass of all the bodies. And so the book has been using the tildes. I like to use this notation. The x-coordinate of the center of mass of each individual body, I for individual. Y tilde equals what I call y sub I, and z tilde is what I call z sub I. Whichever notation you feel most comfortable with.